Hello everyone, welcome to Sigmoid Tech Talk. My name is Ankit Sharma and I'm working as an associate lead data scientist at Sigmoid. Today our topic is gradient descent and we'll discuss more about it. Today we are going to discuss gradient descent with respect to linear regression. Let's go to this next slide and discuss more about it. So first of all, what is linear regression? So basically linear regression is nothing but it's a supervised machine learning algorithms that predicts a dependent variable based on certain independent parameters that are given by the independent variable or are denoted by X value. And the reason it is called as supervised machine learning algorithms because first it trains the data and detects the relationship between your independent and dependent variables. That is why it is called supervised machine learning algorithms. There are multiple advantage or importance of linear regression. The first advantage of or the importance of linear regression is it's very simple to implement because only the one mathematical equation is there, right? It's very easy to understand. The second advantage is it's very easy to interpret the output coefficients or the beta coefficients of your linear regression model. Third advantage of linear regression model is it's computationally very efficient. And the fourth advantage of linear regression is whenever you're facing any issue of overfitting, at that point of time, you can use regression techniques. So these were some of the advantage of linear regression model. I have listed these use cases of linear regression model as well. So majorly there are two major use cases of linear regression model. The first one is the predictive analytics, where any company can use this linear regression model to forecast their inventory or forecast their sales. And then second is the operation efficiency. Operation efficiency can be used where the company can come and streamline their process using the linear regression model. At that point of time, linear regression is very helpful. So these are some of the use cases of linear regression models. Here I have shown a graph where I have plotted a blue line that is the linear regression fitted line, and the red dots which you can see are the data points of actual value. We are going to discuss more into detail about how do we arrive at this particular line and how do we calculate this line, right? Or how do we arrive at this particular the best parameters of this. So we are going to discuss this in the next slide. So here, this blue line, that is the linear regression line, is represented by this hypothesis h of theta equals to theta naught plus theta 1 x, where theta naught is your intercept at y-axis, this value, and theta 1 is your slope of your linear regression, the slope of this particular line, blue line, right? And in linear regression, the cost function is given by this equation, where it is nothing but your uh, predicted value coming from this h of x coming from blue line minus your actual value y of I coming from this red point, whole square of this, right? And the summation of this difference of your predicted and actual value multiplied by 1 by 2m. M is nothing but your number of records in your data. Here we are multiplying it 1 by 2m to average out the summation square value so that your cost function doesn't get impacted by the number of records available in your data. And we are using a square value here because here in cost function we are using mean square error value. That's why we are squaring here, right? Now our ultimate aim here is to minimize this cost function by changing the value of theta. When I'm saying to minimize this cost function, it will be minimized when the difference between your predicted value and your actual value is minimized, right? So this is how we are going to minimize the cost function. In this session, we are going to discuss about convergence theorem and more about gradient descent. Let's go to the convergence theorem. So convergence theorem equation is given by this line, this theta j. This sign is given. This sign is called as the assignee side. Theta j minus alpha times your partial derivation of your cost function, which we have seen in the previous session, for j equals to 1 and j equals to 0. J equals to 0 and j equals to 1 are directly coming from the number of parameters. If you have two parameters, the similar value of j will be there, right? As we have theta 0 and theta 1, that's why j equals to 0 and j equals to 1. Now with each iteration, there are two ways of calculating your thetas. First one is the correct way. We are going to simultaneously update your theta values. First we are going to calculate time 0, So it is going to calculate by theta 0 minus alpha partial derivation of your cost function. In the similar way, we are going to calculate temp1. Once we have calculated both temp0, temp1, we are going to simultaneously update this new theta 0, theta 1 in the cost function and then again iterate it, the same process. The incorrect way would be where first we are going to calculate the temp0 value and then use this new temp0 value while calculating the new temp1 value. So this is wrong. This should not be done. We should always update the theta value simultaneously in nature as shown here. Moving to the next slide. Here in this slide, I have shown you a cost function with respect to the theta 1 values. So the reason I am going to show you this function here, I am keeping theta 0 equals to 0 because I wanted to show you in the 2D image, and it can only be done if I'm keeping theta 0 equals to 0. The reason of showing you this graph, so I wanted to show you how your theta 1 value or a theta 1 values changes when you are going to uh, calculate with each iteration, right? So let's say at this point of time, you have certain theta 1 value that is noted by here. This theta 1 value is here at this point of time. Now, if you calculate the gradient at this point of time, this gradient or the slope is negative in nature, right? So temp1 equals to theta 1 minus alpha time some gradient, right? As we see here, gradient is negative. So minus alpha multiplied by some minus value. So you will get theta 1 plus some value. So temp1 will be greater than theta 1 value. So your temp1 will move here as you can see your theta has increased now. In the similar way, if you keep on iterating, your theta will increase and it will come at this point of time, at this point, right? Here, your cost function will be minimum. In the similar way, if you see theta 1 here and you calculate the gradient here or the slope here, your gradient will be positive in nature. So minus alpha multiplied by some positive value, so this whole thing will be minus only. So theta 1 minus some positive value. So temp1 will be less than your theta 1, right? So that's why your theta is decreasing. In the similar way, if you keep on iterating, your theta 1 value decreases and it will give you the optimal value of theta that will give you the minimum cost function. And this parameters theta 1 is the right parameter for your linear regression line, blue line, which we discussed earlier. In this session, we are going to cover the learning rate, how does it affect the your theta parameters, and all about the different types of gradient descent algorithms. So let's go in this slide. So here, as we can see in convergence theorem, we have one parameter alpha. This alpha is called as the learning rate parameter of the equation gradient descent, right? And this alpha value is decided how your theta values with each iteration is going to change. And the values of alpha lies from 0 to infinity. It can be anything. And to arrive at the optimal value of alpha, you will need to iterate through it different with different values. And most optimal value will give you the right value of alpha only, right? Here in 3 graphs, I have shown the cost function and the theta parameters, how it's going to change when you are keeping your alpha value very low, when you are going to keep alpha value very high, and when you are just keeping the right value of alpha. So let's look at when you are keeping the very low value of alpha. So if you are keeping a very low value of alpha at that point of time, with each iteration, your theta values is going to change very small, right? So because of this, it is going to take a lot of time to converge, right? So it's not the optimal solution because it's going to take a lot of time as well, and it's computationally expensive at all as well. So that's why it's not recommended. In the similar way, if your alpha value is very high, at that point of time only, your theta values are going to change very drastically, and there are chances that you might not reach to the optimal value of your cost function, or your theta values are going to overshoot because of high value of alpha. So that is also not recommended. So if we are keeping the right value of alpha, in that case your theta's value is going to change very smoothly, and you will very smoothly arrive at the very minimal value of your cost function, and that is what's the right or the optimal value of your alpha value, right? So this is what about the learning rate parameter or the alpha value. Now we are going to cover different types of gradient descent in the next slide. So Here we have three different types of gradient descent algorithm. The first is the batch gradient descent algorithm. The second is the mini-match gradient descent algorithm, and third is the stochastic gradient descent algorithms. So the main difference between all these three algorithm is the number of records which you are going to use while calculating the cost function. Right? In batch gradient descent, you are going to use all the records which are available in your database to calculate the cost function. In the mini-match gradient descent, you are going to use slightly less number of records available in your data to calculate the cost function. Whereas in your stochastic gradient descent, you are going to consider only a single data point while calculating the cost function. So as the number of records changes while calculating the cost function, so there are some advantage and there are some disadvantage associated with all these three methods, right? So first I'm going to covering the batch gradient descent algorithms. So as we know that we are going to use all the number of records in our database, so because of this algorithm is going to be computationally slow and it's going to be expensive, right? But it will main advantage of this equation is it will always give you the optimal solution because it will always reach to the global minima value. That's why it is very advisable if you have less number of records in your database, use batch gradient descent algorithms. Then coming to the minimatized gradient descent algorithms, it is computationally between batch and stochastic gradient descent algorithms because it is going to use less number of record as compared to the batch gradient descent, but more number of record as compared to the stochastic gradient descent. It is also going to give you the optimal solution, and it will also reach the minimum global minima value. And for stochastic gradient algorithms, it is computationally faster and non-expensive because it is going to use only a single data point while calculating the cost function. The main disadvantage with stochastic gradient descent algorithm is it is providing you the good solution, but it will not give you the optimal solution because it will never reach the global minima value here. It will always oscillate around the global minima value, but it will never touch the your global minima value of your cost function. So that's why the optimal solution is not there for stochastic gradient descent algorithm. So this was all about the gradient descent algorithms. We started with the linear regression model, then covered the convergence theorem and the gradient descents. And here in this slides, we are covering the different types of gradient descents. This was all about this particular topic. Thank you, everyone, and have a nice day. Thank you.